Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats. Let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know quickly in the chats with some fire emojis. If all of you can hear me, if I am perfectly audible and visible to every one of you. Quickly, my dear students. Well, today we are going to complete the chapter Atomic Structure. I had already posted one video, which was the part 1 of the atomic structure, right? Wherein, in that particular session, we completed almost like, I would say 70 to 80% of the chapter. The remaining part we are going to complete in the today's session. So today it's going to be the last session of the atomic structure. Okay? And a lot of students were asking me, where can they find exactly the atomic structure part 1? My dear students, what exactly you need to do, this is a channel which you are following. You just need to go to the playlists. You just need to go to the playlists. And once you click on the playlist, just drag it a little down. Here you can find complete chemistry NEET 25-26 view playlist. And here is the atomic structure part 1. Here is the atomic structure part 1, right? Okay. The ones who did not study atomic structure part 1 yet, I would want you guys to go to this particular video. This is the atomic structure part 1. And this is, I believe, 7 hours long. This is, I believe, 7 hours long, this particular session. And here you can complete your part 1 of the atomic structure. And today it's going to be the part 2, wherein we shall be completing the whole chapter. So all ready for it? All ready for it? Yes, Maharan, I got to know. All ready, people? Let me know quickly in the chats. All ready? So first of all, let me know in the chats whether you guys are done with part 1 or not. How many of you are done with part 1? Yes, Lavanya, that it's going to be sufficient for BitSat as well. Let me know in the chats how many of you are done with the part 1. And my dear students, one more thing I forgot to tell you. What is that? The next chapter which we shall be starting here on this particular channel, that is going to be your chemical bonding, right? Chemical bonding is going to be the next chapter which we shall be starting on this particular channel. And the first session of chemical bonding will happen day after tomorrow. Okay, day after tomorrow. On 14th of August, we shall be doing this particular chapter, that's chemical bonding. And I shall be completing this particular chapter exactly in 3 sessions, not more than that. Okay? So, should we start the session then? Should we start the session? So, let me first of all tell you what all things we need to cover in the today's session. Have a look, people. So let me tell you exactly what all things we shall be covering in the today's session. The first topic that we shall be discussing, that's going to be Heisenberg's uncertainty principle. This is the first topic that we shall be doing. After doing the Heisenberg's uncertainty principle, then my dear students, we shall be going into the quantum numbers. Okay. Once we are done with the quantum numbers, we shall be discussing about the shapes of the orbitals. And once we are done with the shapes of the orbitals, then we shall be talking about the nodes, their calculation, followed by probability distribution diagrams. And at the end, we shall be discussing about the electronic configuration as well. So, these are basically the set of the topics which we are going to cover in the today's session. Okay, these are the set of the topics which we shall be covering in the today's session. Rest all the topics in the atomic structure, they are covered in the part 1. How long this class will be? The class will be for almost like 2 hours. Yes, in 2 hours we'll be done with this particular chapter. Okay. In 2 hours we'll be done with this particular chapter. And the ones who have not liked the session yet, I would want every one of you to smash the like, right? Do share this particular video with everyone whosoever is preparing for either NEET 2025 or 2026, right? Do share this with everyone. Okay? And the ones who have not subscribed to the channel yet, I would want every one of you to subscribe to this particular channel as well. Okay? So people, let's get going then. Let's get started and let's turn the dark mode on. Yeah, the dark mode is on. All right. All right, guys. I'm marking the heading over here as Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. Let's first of all get to know what this principle exactly is all about and what kind of questions can be asked from this particular principle. Okay? So my dear students, I'm writing its statement first of all. As per the Heisenberg's uncertainty principle is concerned, I would say the exact momentum and the position. The exact momentum and the position of a microscopic particle. Like electron, cannot be determined simultaneously with 100% accuracy. This is the simplest statement of the Heisenberg's uncertainty principle. My dear students, whenever you'll be having a microscopic particle like electron, you cannot locate its position and momentum simultaneously. You cannot locate its position and momentum simultaneously with 100% accuracy. What does that mean? Just give me a second, guys. Just give me a second. Be like this. Okay. So what is meant by this particular statement? Before letting you know exactly what this statement is all about, let me tell you one more thing. Before making you understand this particular statement, let me tell you one more thing. Let me write one more statement. If we try to determine the position of the microscopic particle like electron, there will be error or uncertainty. There will be error or uncertainty in its momentum. And vice versa. Now, what exactly is meant by this particular statement? What is meant by these two statements? Guys, this is super important. Now, let's try to understand what exactly it means. Okay? In order to make you understand this Heisenberg's uncertainty principle, I'll be asking you a question. I'll be asking you one simple question. How do you exactly see the objects? How do you see the objects? You would have studied that in your class 10th in the chapter light. How do you see an object? It is entirely based on the reflection of light phenomenon. It's entirely based on the phenomenon of the reflection of light. For example, how do I see this phone over here? The reflection of light says that light strikes this object and the reflected ray makes the image on my retina. That's a simple phenomenon. So in order to see an object, first of all, light has to be incident on that object. Light has to be incident on that object. And once the reflected ray comes back, that reflected ray should make an image, right, in the retina. So that's how you see exactly the object. Now, why am I telling you that? For example, I'm asking you, how do I see this marker? How do I see this marker? Basically, light is incident on it, and the reflected ray, that's making the image on my retina, etc., etc. That's the common phenomenon based on, that's the common phenomenon by means of which we exactly see the objects, right? Now try to understand. For example, this is the nucleus. Let's say this is the nucleus, okay? Let's say these are the shells. Let's say these are the shells. Perfect. Now, for example, electron is revolving in this particular shell. Let's say electron is revolving in this particular shell. Okay. For example, my dear students, imagine that I want to see this electron. Imagine that I want to see this electron. Now, the first thing that comes into my mind, if I would want to see this electron, the first thing that comes into my mind, that is the reflection of light. I'm considering that I'll put light on this electron. And once the light strikes on the electron, it will get reflected back. And this reflected light I can see over here. That's how I can see the electron. That's how I can locate the electron. This is the first thing that comes into my mind if I want to locate this electron. If I want to locate this electron, if I want to see this electron, if I want to locate its position, I'm assuming that some light I'll put on this particular electron and light will get reflected back. And then I'll see that reflected ray and eventually I'll see the electron. But my dear students, if you think logically, since light is incident on this electron, what is light? What is light? What is light? Energy. So basically light is incident on this electron. So energy is incident on this electron. And we know when energy is incident on the electron, what's going to happen? What's going to happen? The electron is going to absorb that energy. And when electron absorbs that energy, the speed with which electron was moving, now the electron will be moving with different speed after absorbing that energy. Right? That's something which is going to happen. So, I wanted to locate the electron. I wanted to see the electron with the help of the phenomenon of light, with the help of the reflection of light. But what happened exactly? What happened exactly? When I wanted to see the electron, some light rays were incident on this electron. What this electron did, it absorbed that energy and it started moving with different speeds now. So if you want to locate the electron, if you want to locate the position of the electron, there will be error in its velocity. And if there is error in velocity, you know, momentum is equal to mass into velocity. If there is error in velocity, that automatically tells you that there will be error in momentum. Right? There will be uncertainty. There will be error in the momentum. Perfect. So if you want to locate the position of the electron, at the same time, there will be error in its momentum. Okay. I can say it like this. I can say it like this. I wanted to locate the electron. That is the reason why this light ray was incident on this electron. But this electron absorbed the light ray. It absorbed the energy and started moving with greater speed. I can say it like this as well. It started moving with greater speed. So when I tried to locate the position of the electron, there was error in its momentum. Right? Similarly, when you try to find out the momentum of the electron, there will be error in its position. So, momentum and position of a microscopic particle like electron cannot be calculated simultaneously with 100% accuracy. If you want to locate the position, there will be momentum, there will be error in the momentum. If you want to find the momentum, there will be error in its position. So both you cannot calculate simultaneously with 100% accuracy. If you would want to calculate one, there will be error in another one. Right? As simple as that. As simple as that. Yeah? Is it clear? Is this point clear to everyone? Is this point clear to everyone, my dear students? So, according to this principle, the momentum and the position of a moving electron cannot be determined simultaneously with 100% accuracy. Okay? If we try to measure momentum accurately, error will occur in the position, right? And if we try to get the position of the electron, there will be error in its momentum. That's all. That's all, right? So both the things cannot go hand in hand. Perfect. Now guys, this error in position I'm representing by delta x. Delta x is something which I call as error or uncertainty in the position. Error or uncertainty in the position of the microscopic particle like electron. Okay. Similarly, delta V. What is delta V? Delta V I'm calling as error or uncertainty in the velocity of the electron. Of the microscopic particle like electron, right? Similarly, delta P. Delta P, you know, your momentum. P is equal to m multiplied by V. Error in momentum will be due to error in velocity, right? So your delta P, which is basically equal to m delta V, right? It represents error or uncertainty. Error or uncertainty in the momentum of the microscopic particle. In the momentum of the microscopic particle, right? Similarly, my dear students, if I write over here a term delta lambda, what is lambda? Lambda is de Broglie's wavelength. You know, lambda is equal to h upon mv. Lambda is equal to h upon mv. That's something all of you would be knowing. Now, my dear students, h is constant, m is constant. So, if I ask you about error in de Broglie's wavelength, can I say error in de Broglie's wavelength will be due to the error in velocity? Error in de Broglie's wavelength will be due to the error in velocity, right? So delta lambda, error in de Broglie's wavelength is equal to h upon m delta V. And this delta lambda is something which you call as error in de Broglie's wavelength. Okay? These are some terminologies which I would want you guys to remember from now onwards. Delta x, delta V, delta P, and delta lambda. Okay? So, again, if I ask you, what is Heisenberg's uncertainty principle? Simply, we cannot determine the exact position and the momentum of a microscopic particle simultaneously with 100% accuracy. If we want to locate the microscopic particle, at the same time, there will be error in its momentum. If you want to find the momentum of the microscopic particle, at the same time, there will be error in the position. So both of the things, position and momentum of the microscopic particle, cannot be calculated simultaneously with 100% accuracy. Okay? With 100% accuracy. If we try to measure the momentum accurately, there will be error in the position. If you want to calculate the position, if you want to locate the position of the microscopic particle accurately, there will be error in the momentum. So both cannot be calculated simultaneously with 100% accuracy. Okay? Now, there are a few results, my dear students, which you need to know. Right? Remember, it has been observed that error in the position of the microscopic particle multiplied by error in the momentum, their product is always greater or equal to h upon 4 pi. Okay, this is one result which you have to remember directly. This is one result which you need to remember directly. Now, my dear students, are there any other results? Yes, there are some other results as well. Since you know, your delta P is nothing but, error in momentum is nothing but, it is m delta V, correct? So, delta x I'm writing as such, delta P I'm writing as m delta V, it is greater or equal to h upon 4 pi. So, I can say delta x dot delta V, it is greater or equal to h upon 4 pi m. This is one more result which you need to remember. Error in the position of the microscopic particle multiplied by error in the velocity of the same microscopic particle, it will be always greater or equal to h upon 4 pi m. So how many results we got till now? We got 2 results, right? And one more result, I'm not going to derive that, right? I'll directly give you an expression and you are going to remember that, and I'll show you how do we use that expression. Okay? My dear students, that expression is in terms of de Broglie's wavelength. Delta lambda dot delta x, it is greater or equal to lambda square divided by 4 pi. It is greater or equal to lambda square divided by 4 pi. Remember this particular expression of the Heisenberg's uncertainty principle as well. These are the three results which I would want you guys to remember from now onwards, right? When it comes to the Heisenberg's uncertainty principle. Delta x delta p is greater or equal to h upon 4 pi. Delta x dot delta v is greater or equal to h upon 4 pi m. Delta lambda delta x is greater or equal to lambda square divided by 4 pi. Okay? Right? Now, my dear students, this Heisenberg's uncertainty principle, let me tell you, this is the main reason why your Bohr's model got flopped. Heisenberg's uncertainty principle was this was the drawback of the Bohr's model. Now you must be thinking, how come this Heisenberg's principle, it is going to be the drawback for the Bohr's model? Understand. Bohr could not explain this Heisenberg's uncertainty principle. Now, how come it's going to be basically the drawback for the Bohr's model? See guys, understand properly what I'm going to say. What Bohr exactly said? Bohr said that electron is revolving around the nucleus in the circular orbit. This is what he told. Electron is revolving around the nucleus in the circular path, right? Which have got fixed energy, fixed radius, and he called these paths as the orbits. These are what you call as energy states, orbits. Okay? Now, my dear students, if I ask you, how exactly can you say that electron is moving in the circular orbit? How can you exactly define the trajectory of the electron? Well, let me tell you, see, let's say there is an object. This is the object. Okay? When can I say that the object is showing the translational motion? When can I say that the object is following this path? I can only say that the object is following this path if at every point of time I know the position and the momentum of the electron of this particle accurately with 100% accuracy. For example, there is an object. There is a very, very microscopic particle, right? That's moving. How can I say that microscopic particle is moving in a straight line? This is the microscopic particle. How can I say it's following this particular path? If at every point of time, if I can locate the position and the momentum of this particle simultaneously with 100% accuracy, then only I can say this particle is moving in the straight line. Then only I can say this particle is following this path. Similarly, how can you say that the electron is revolving around the circular path? How can you say that electron is revolving in this particular path? How can you say that the electron is following this particular path? You can only say that if you exactly know the position and the momentum of the electron simultaneously with 100% accuracy at every point of time. But that's impossible. You cannot calculate the position and the momentum of the microscopic particle like electron simultaneously with 100% accuracy. We got to know about that, right? So Bohr could not explain this particular point. He could not explain this particular point. Okay? Is this point clear to everyone? Say yes or no in the chats quickly. Say yes or no in the chats quickly. Quickly, people, everyone in the chats, if this is clear. Yes, even JEE aspirants can also watch it, no issues. So I hope you got to know what was exactly the failure of the Bohr's model. Yeah? Bohr exactly told us that the electron is moving in the circular path. But how can you say that the electron is moving in the circular path? How can you define the trajectory of the electron? In order to define the trajectory of the electron at every point of time, you should know the position and the momentum of the electrons simultaneously with 100% accuracy, but that's not possible. Right? So you cannot say that the electron is here, electron is here, electron is here, electron is here, electron is here. You cannot say like that. Okay? Therefore, what came into existence? Therefore, what Heisenberg said, Heisenberg said we can only define the probability. We can only define the probability of finding the electron around the nucleus. Right? Let's say this is the nucleus. We can say at some point of time electron should have been here. At some point of time electron would be here. At some point of time electron would be here. At some point of time electron would be here. Right? So now, from now onwards, we'll be talking in terms of probabilities. We'll talk in terms of probability of finding the electron around the nucleus. Right? We'll talk in terms of probability of finding the electron around the nucleus. Okay? So according to Heisenberg, you cannot exactly say that electron, you cannot say with 100% accuracy that electron is here. No, you can say, you can talk in terms of probability of finding the electron here, probability of finding the electron here, probability of finding the electron here, around electron here, right? So let me first of all tell you, from now onwards, we are going to talk in terms of probabilities of finding the electron. Okay? Right? Perfect. So this was the main drawback of your Bohr's model. Now, the point is, what kind of questions are asked from your Heisenberg? What kind of questions are asked from your Heisenberg? Look at the first question. Look at the first question, guys. The first type of the question. A particle with mass. You have got a particle which has got a mass of how much? 10 raised power minus 10 grams. Right? Which will be 10 raised power minus 13 kilograms. Right? Which will be 10 raised power minus 13 kilograms. Okay? You have got the particle of mass this much. If the particle is moving with the velocity of how much? 10 raised power minus 6 centimeter second inverse. The particle is moving with this velocity, 10 raised power minus 6 centimeter per inverse. It means the particle is moving with 10 raised power minus 8 meter per second. Divided with 100. Okay? Now, the particle is moving with the velocity of this much, with this much percentage of uncertainty. With this much percentage of uncertainty. With this much percentage of uncertainty. So, how much is the uncertainty in the velocity? This term, 0.0001% of what? Of 10 raised power minus 8. Right? This much is the uncertainty in the velocity that's given to me as per the question. Right? This much is the uncertainty in the velocity that's given to me in the question. What are we supposed to calculate? We are supposed to calculate delta x. We are supposed to calculate delta x. We are supposed to calculate error in the position. Is there any equation that is relating all these terms? Is there any equation that is relating all these terms? Yes, there is one equation which I gave you a few minutes back. You know, delta x dot delta v, it's greater or equal to h upon 4 pi m. Now, for calculation purpose, I'm not going to use greater or equal to. For calculation purpose, I'll be using just equal to sign. Okay? Now, delta x I need to calculate. Delta x is equal to h upon 4 pi m multiplied by delta v. What is the value of h as per SI system? 6.6 into 10 raised power minus 34. Use all the terms as per SI system. That is the reason why I converted mass into kilograms as per SI system. That is the reason I calculate velocity into meter per second as per SI system. Right? So, it's going to be 4 pi value is nothing but 22 by 7. Mass of the particle is nothing but 10 raised power minus 13. And delta v, error in the velocity, that's equal to how much? Error in the velocity is given to me as 0.0001 multiplied by 10 raised power minus 8 divided by what? Divided by 100. This is the term which you have to solve, and you'll be getting the error in the position as per SI system only. You'll be getting error in the position as per SI system only. That means you'll be getting the error in the position in meters only. So this is the first type of the question, which is directly going to be the formula based one. Okay? Right? Let's have a look on the second type of the question that can be asked here. This is the second type of the question, my dear students, which can be asked. The question is, An electron is accelerated from rest by applying a voltage of 6 volts. If delta x is equal to 7 by 22 nanometer, then calculate delta lambda. We have to calculate delta lambda. Is there any equation? Is there any equation wherein delta lambda was introduced? I gave you one equation if you remember. Delta x dot delta lambda, it is greater or equal to lambda square divided by 4 pi. Right? This is one equation which I gave you a few minutes back. This is one equation which I gave you a few minutes back. So my dear students, what am I supposed to calculate? I'm supposed to calculate delta lambda. For calculation purpose, I'll be using the equal sign. So this lambda square divided by 4 pi multiplied by delta x. Multiplied by delta x. Okay? Multiplied by delta x. Now, how do I get lambda over here? See, delta x is given to me. How do I get the lambda? That's the point. How do I get the lambda? Since, my dear students, electron is accelerated from the rest. And whenever electron is accelerated under the potential difference of V, how do you calculate lambda? If you remember, there is a formula 12.27 divided by under root of V angstroms. This is the formula for the electron. When electron is accelerated under the potential difference of V, this is how you calculate its lambda. Okay. Now, my dear students, just put the value of V over here. Electron is accelerated at 6 volts. Okay. When you solve this, you'll be getting the value exactly as 5 angstroms. Use SI system. So 5 into 10 raised power minus 10 meters. Right? This is the value of lambda which you got. This is the value of lambda which you got. Okay. Now, we are almost done. So delta lambda is equal to lambda square. So 5 into 10 raised power minus 10 ka square divided by 4 multiplied by pi is 22 by 7. And your delta x is 7 by 22 nanometer, which is 10 raised power minus 9 meters. Right? Because I told you, whenever you use these sort of equations, you will be using all the parameters as per SI system. Okay, you'll be using all the parameters as per SI system. That's why 1 nanometer, you know, it's 10 raised power minus 9 meters. So multiplied it with 10 raised power minus 9. Now, eventually, it's just the matter of calculation. And you'll be getting the answer exactly in meters. Because I used all the parameters as per SI system. So delta lambda, you'll be also getting as per SI system only. Okay. This was one more type of the question that can be asked. Now, it's just a matter of calculation, nothing else. You'll be getting delta lambda here. For example, you have a question like this. If the error in velocity and the position are same, understand, if the error in velocity and position are same, error in velocity and position, they are given same. Calculate the error in de Broglie's wavelength. Error in de Broglie's wavelength is represented by delta lambda. We have to get the delta lambda value. We have to get the delta lambda. And you know, delta lambda is nothing but it is h upon m delta v. It is h upon m delta v. So in order to get delta lambda, what do I need? I need the value of delta v. Once I get the value of delta v, I'll put it here, get the value of delta lambda. And how exactly I'm going to get it? Understand. I gave you one result. Delta x dot delta v, it is greater or equal to h upon 4 pi m. Right? For calculation purpose, I'll be using only equal sign over here. Now, as per the question, delta v and delta x, they are equal. If delta v and delta x are equal, I'll be writing delta v ka square is equal to h upon 4 pi m. Simple. So delta v will be equal to under root of h upon 4 pi m. This is your delta v here. This is your delta v here. Now, my dear students, if you got the delta v, put it here. You're done. So delta lambda is equal to h upon m, and your delta v is nothing but it's under root of h upon 4 pi m. Under root of h upon 4 pi m. Right? Now, let's try to simplify it a bit. So delta lambda is equal to, if I take root common, this was h. Inside the root, it becomes h square. Then only square root that's cancelled and h comes out. Right? Divided by. This was m without the root. Now, inside the root, it's going to be m square. Inside the root, it's going to be m square. This h was already in the root, and this 4 pi m was already in the root too. Now, see what all things will get cancelled out. You'll be getting this h and h got cancelled. Okay. One of the m got cancelled out. Okay. What do I get at the end? It's going to be under root of 4 pi h divided by m. This is the final answer of the question. This is going to give you the error in the de Broglie's wavelength. That's something I was supposed to calculate. Am I clear with this? This is one more type of the question that can be asked here from the Heisenberg's uncertainty principle. Is that clear, guys? All clear? All clear, all clear? All clear, quickly. I believe everything is clear till here. And these were the set of the questions that can be asked from the Heisenberg's uncertainty principle. I hope you got to know what Heisenberg's uncertainty principle is all about, number one. Number two, I hope you got to know how come it was the drawback, major drawback of the Bohr's theory. I hope you got to know how come it was the major drawback of the Bohr's theory. Because Bohr exactly told that the electron is moving in this circular path. You can only say that the electron is moving in this circular path if at every point of time you know the exact position and the momentum of the electron simultaneously with 100% of accuracy, which is not possible. So you cannot exactly say that the electron is moving this path, electron is moving in this path, electron is moving in this path. No. Therefore, you talk in terms of probabilities. You talk in terms of probability. Okay? From now onwards, we'll use the term probability of finding the electron around the nucleus. Okay? All clear? All clear, people? Now comes one more important topic, that is your quantum numbers. Okay, just a second. Just a second. Now comes your one more important topic, that is your quantum numbers. So, what these quantum numbers exactly are all about? Let's try to understand. Let's try to understand what these quantum numbers are all about. My dear students, quantum numbers, let me tell you, these are the set of numbers. These are the set of numbers which give all the information, about an electron, in an atom. So quantum numbers, which we are going to discuss, these are going to be the set of the numbers. These are going to be the set of the numbers, my dear students, which are going to give us all the information about the electron in an atom. Now, what kind of information? That's something which you are going to understand here. Okay. Now, so first of all, before talking about them in detail, if I ask you how many quantum numbers do we have? The first one is your principal quantum number. The first one is your principal quantum number, represented by n. Second one is your azimuthal quantum number, or you call it as the subsidiary quantum number. You represent this with L, right? Azimuthal quantum number. Then comes your magnetic quantum number. Magnetic quantum number, represented by M. Then comes your spin quantum number. Then comes your spin quantum number, represented by S. Okay. Now, how many quantum numbers do we have? We have got 4 set of numbers which are going to give us the complete information about an electron inside the atom. Okay. The first point which I'm going to tell you, the first 3 quantum numbers, your N, L, and M, these are the outcome. These are the outcome of Schrodinger's wave equation. Remember this particular point. In total, we have 4 quantum numbers, but out of 4 quantum numbers, the first 3 quantum numbers, N, L, and M, they are the outcome of the Schrodinger's wave equation. They are the outcome of the Schrodinger's wave equation. Spin quantum number, this is not the outcome of Schrodinger's wave equation. Remember this particular point. This can be asked directly. This can be asked directly. Which of the following is not the outcome of the Schrodinger's wave equation? Spin quantum number is the one. which is not the outcome of the Schrodinger's wave equation. Okay. Now guys, let's try to understand these quantum numbers one upon one. See guys, let's talk about the principal quantum number first. First of all, this principal quantum number, what kind of information it gives us? My dear students, this principal quantum number, it gives the idea about the size and the energy of the shell. So basically, the principal quantum number, let me write it over here. Principal quantum number, which is your n, it gives an idea about the shell number. It gives the idea about the shell number in which electron is present. It gives an idea about the shell number in which electron is present. You know, when I talk about the shells consist of subshells and subshell consists of orbitals. So principal quantum number is going to let us know in which shell electron is present. In which shell electron is present. Okay? This is going to let us know in which shell electron is present. Number one. Number two. This n can have different values. N can have value 1, n can have value 2, n can have value 3, n can have value 4. N is equal to 1 represents the first shell. That is what you call as K shell. N is equal to 2 represents your second shell, which is designated as L shell. Similarly, n is equal to 3. It represents your M shell. N is equal to 4 represents your N shell. So, the principal quantum number, it gives me the information about the shell number in which electron is present. If the electron is present in third shell, you'll directly say n is equal to 3 for an electron. If the electron is present in fourth shell, you'll directly say n is equal to 4 for the electron, right? Okay, so principal quantum number particularly gives me the idea about the shell number in which electron is present, number one. Number two, it gives me the idea about the size and energy of the shell as well. It gives me the idea about the size and the energy of the shell as well. Okay, and you know, as the value of n increases, size as well as energy of the shell increases. How can you relate it? In the Bohr's theory, you have studied radius of nth orbit is equal to r naught n square divided by z, right? Similarly, energy of the nth Bohr's orbit, do you remember? It used to be minus 13.6 z square divided by n square. Okay, have you studied these results? In the first session, you would have studied, right? In this result, do you see n? Yes. In this result, do you see n? Yes. Perfect. And we have discussed in detail, as the value of n increases, the size of the shell increases. As the value of n increases, energy of the shell increases. Okay? That can be explained with the help of these two results which are mentioned over here. Perfect. So my dear students, just one thing I would want you guys to remember here. The principal quantum number, it is going to give me the idea about the shell number in which electron is present, right? And if you ask me the maximum number of electrons that can be present in a shell, it is given by 2n square. It is given by the formula 2n square, right? So in the first shell, how many maximum electrons can be accommodated? Put the value of n as 1, so 2 electrons maximum, right? In second shell, put the value of n as 2, 2 ka square is 4, 4 2s are 8, right? In the third shell, 3 ka square 9, 9 2s are 18, right? In the fourth one, 4, 4, 16, 2, 32. So the maximum number of electrons that can be accommodated in first shell, second shell, third shell and fourth shell are respectively 2, 8, 18, 32 respectively. Okay? So this is just the information which you need to remember about the principal quantum number. That's all. Nothing more than this. In short, principal quantum number, it's going to give me the idea about the shell number in which electron is present. Okay? Now comes the important one. What is that? What is that? That is the azimuthal quantum number. This is somewhat important, right? My dear students, I told you shells consist of subshells. Subshells consist of orbitals. And electrons at the end are present in the orbitals. That's what we say, right? Principal quantum number gave us the idea about the shell number in which electron is present. Now, azimuthal quantum number is going to give us the idea about the subshell of a particular shell in which electron will be present. So, it represents the subshell within a shell. It represents a subshell within the shell, right? Shape of the subshell we'll be discussing after some time. Okay? Each value of L represents a subshell. For a given value of n, there are 0 to n minus 1 L values. What exactly is meant by all this stuff? Try to understand. I'm talking about the azimuthal quantum number. I'm talking about the azimuthal quantum number, which is represented by L. Okay? So my dear students, the first thing which I want you guys to remember from now onwards, azimuthal quantum number, it's going to give me the idea about, it is going to give me the idea about the subshell in which the electron is present. It gives me the idea about the subshell in which the electron is present, right? Now, let me tell you, every value of L represents what? Represents a subshell. Every value of L represents a subshell. Every value of L represents a subshell. Now, this L, it can have values from 0 to n minus 1. This L can have values from 0 to n minus 1. My dear students, remember, if L is equal to 0, L is equal to 0 represents your S subshell. L is equal to 1 represents your P subshell. L is equal to 2, it represents your D subshell. And L is equal to 3, it represents your F subshell. It represents your F subshell. For example, let's say I'm talking about n is equal to 1. N is equal to 1 means the K shell, the first shell. The first shell. Okay? N is equal to 1 means the first shell. Now, if n is equal to 1, what will be the possible values of L? For n is equal to 1, put the value of n as 1 here. So 1 minus 1, 0, 0 to 0. L is equal to 0. L is equal to 0. L is equal to 0 represents which subshell? It represents your S subshell. So basically, I can say, in your first shell, there will be only one subshell. That's something which you call as S subshell. In your first shell, there will be only one subshell. That subshell is what you call as S subshell. Right? Right, people? Now, similarly, for n is equal to 2, if n is equal to 2, that means which shell I'm talking about? I'm talking about the second shell, L shell, right? If n is equal to 2, L can have how many values? L is 0 to n minus 1. So 0 to 2 minus 1. 2 minus 1 is 1. So L can have value 0, it can have value 1. I told you, every value of L represents a subshell. Every value of L represents a subshell. So this is one of the values of L, this is one of the values of L. And L value 0, it represents your S subshell. And L value 1, it represents your P subshell. Perfect. So can I say in the second shell, there will be two subshells? One is going to be your S subshell and one is going to be your P subshell. In the first shell, there was only one subshell. In the second shell, there are two subshells, S as well as P. Now, talk about the third shell. Talk about the third shell. Third shell means M shell. If n is equal to 3, how many possible values of L will be there? How many possible values of L will be there? 0 to 3 minus 1. 3 minus 1 is 2. So 0 to 2. 0 to 2 means it can be 0, it can be 1, it can be 2. So how many L values you are getting here? You are getting 3 values of L. And every value of L represents a subshell. So this represents your S subshell, this represents your P subshell, and this represents your D subshell. So can I say the third shell consists of how many subshells? The third shell consists of 3 subshells. S subshell, P subshell, and D subshell. Similarly, if you talk about n is equal to 4, if you talk about n is equal to 4, now where exactly am I going to write that? Let me write it here. N is equal to 4. Fourth shell. Fourth shell means n shell. How many possible values of L can be there? 0 to 4 minus 1. 0 to 4 minus 1. 4 minus 1 is 3. So it can be 0, 1, 2, and 3. So how many L values did you get over here? You got 4 L values. And every value of L represents a subshell. So how many subshells do you have? You have got 4 subshells here. This represents your S subshell. This represents P. This represents D. And this represents F. Okay. So basically in your first shell, there will be one subshell. Second shell consists of 2 subshells. Third shell consists of 3 subshells. And fourth shell consists of 4 subshells. right? Perfect. Right, people? If I say something like this, for an electron L value 0, if I say for an electron L value 0, what does that mean? That means the electron is present in the S subshell of some of the shell, right? Right, people? Perfect. Perfect. I believe this is clear. I believe this is clear. This is something which I was telling you till now. In the first shell, only one subshell. Second shell consists of two subshells. Third shell, three subshells. Fourth shell, four subshells. S stands for sharp, P stands for principal, D stands for diffuse, F stands for fundamental. Right? The SPDF terms which you use over here, right? These are their full forms. I hope I'm clear with this. I hope I'm clear with this. Now, what kind of extra information? What kind of extra information? What kind of extra information we can get from the azimuthal quantum number? Is there any extra information which we can get from here? Is there something else which we can get from the azimuthal quantum number? Yes. Yes, there is something extra as well. Okay, what is that extra thing? Sometimes you get a question based on orbital angular momentum. Sometimes you get question based on orbital angular momentum. And there is a formula by means of which you can calculate the orbital angular momentum, which entirely depends on the L value. Orbital angular momentum is equal to under root of L into L plus 1 multiplied by h upon 2 pi. Under root of L into L plus 1 multiplied by h upon 2 pi. For example, let's say I've got 1s. Let's say there is 2s. Let's say you've got 2p. Let's say you've got 3s. Let's say you've got 3p. Let's say you've got 3d. These are the, for example, different subshells which I have. Now I want to calculate their orbital angular momentum. Orbital angular momentum of 1s. In case of 1s, what is the n value? N value is 1. I've got nothing to do with the n value. What is the value of L for S subshell? The value of L is 0 here. What is the value of L for S subshell? It's again 0. What is the value of L for P subshell? It's 1. Over here, 0. Over here, L value is 1. Over here, L value is 2. So you got the different L values, right? Since you got the L values, now what you're supposed to calculate? Orbital angular momentum. Orbital angular momentum here will be under root of L into L plus 1. L value is 0, right? So entire term comes out to be 0. So for 1s, orbital angular momentum is 0. Similarly, for 2s, orbital angular momentum will be 0 because again L is 0. Now, for 2p, for p, what will be the orbital angular momentum? Under root of L into L plus 1. 1 plus 1 is 2. So, root of 2 h upon 2 pi. This can be written as under root of 2 h upon 2 pi. Or finally, you can write it as h upon under root 2 multiplied by pi. Right? Perfect. As simple as that. Similarly, let's say you have got 3s. L is 0. So, orbital angular momentum has to be 0. Done. 3p. L is equal to 1. If L is 1, your orbital angular momentum again comes out to be the same. That's h upon under root of 2 multiplied by pi. Similarly, D. In case of D, L is 2. If L is 2, the orbital angular momentum is equal to under root of L into L plus 1 multiplied by h upon 2 pi. So, 2 plus 1 is 3. 3 2s are 6. So, root of 6 multiplied by h upon 2 pi. This is going to be your orbital angular momentum in case of your D. Perfect. So I believe if a question is asked based on the orbital angular momentum, you should be in a position to solve this question on your own. Okay? On your own. Perfect, guys. Now, after talking about the azimuthal quantum number, it is the time to talk about the magnetic quantum number. But before that, one thing, guys. The first shell contains only one subshell. Second shell contains two subshells. Third shell contains three subshells. Fourth shell contains four subshells. So, for a given value of n, how many subshells will be there? there will be n subshells. So number of subshells. This exactly means number of subshells in a particular shell. Number of subshells in a shell is equal to the value of n. Whatever is the n value, same number of subshells you can find in a shell. Simple. Done and dusted. Okay? Perfect. So let's move on to something which is what you call as magnetic quantum number. Okay? What this magnetic quantum number is all about. My dear students, principal quantum number was giving us the idea about the shell number in which electron is present. Now in the shells you have got subshells. Azimuthal quantum number gave us the idea about the subshell of a particular shell. Now in the subshells, your subshells consist of orbitals. Now this magnetic quantum number, it is going to give us the idea about the orbital. The orbital in which electron is present. It is going to give us the idea about the orbital in which electron is present. Let me first of all tell you, like I told you, every value of L represents a subshell. In the similar way, my dear students, remember, every value of M represents an orbital. Every value of M represents an orbital. Every value of M represents an orbital. And M can have its values from minus L to plus L. Minus L to plus L. What does it mean? See guys, if I talk about S subshell, understand, if I talk about S subshell, in case of S subshell, what is the value of L? L value is 0. If L value is 0, what will be the possible values of M? Minus 0 to plus 0, which means 0. So how many M values did I get? I got one M value, which is equal to 0. And every value of M represents an orbital. So I would say, in the S subshell, there will be only one orbital. And you call that orbital as S orbital. You call that orbital as the S orbital. You call that orbital as the S orbital, which I'm representing like this. Okay? So in your S subshell, there will be only one orbital, which is what I call as S orbital. Now talk about the P subshell. Talk about the P subshell. In the P subshell, if you talk about P subshell, the value of L is 1. If the value of L is 1, what will be the possible values of M? Minus 1 to plus 1. So it will be minus 1, 0 and plus 1. So how many M values did I get over here? I got 3 M values. Every value of M represents an orbital, right? So this value represents an orbital, this value orbital, this orbital. So P subshell consists of how many orbitals? P subshell consists of 3 orbitals, out of which one I'll be calling as Px, one I'll be calling as Py, one I'll be calling as Pz. Right? Simple. One I'll be calling as Px, Py, Pz. Right, people? So 3 orbitals when it comes to P subshell. If you talk about your D subshell, in case of your D subshell, what is the L value? L value is 2. So M can have values from minus 1, minus 2, minus 1, 0, plus 1, as well as plus 2. So how many M values did you get over here? 5 M values. Number of M values is equal to the number of orbitals. Every value of M represents an orbital. So in the D subshell, how many orbitals do we have? In the D subshell, we have got 5 orbitals. 1, 2, 3, 4, 5. Out of which, one will be called as dxy, one will be called as dyz, one will be called as dzx, one will be called as dx square minus y square, one will be called as dz square. After some time, you'll look at their shapes as well, how they look like. In detail, I'm going to let you know about that. Okay? Right, people? Similarly, when it comes to F subshell, for F, L is 3, so minus 3 to plus 3. So 7 different orbitals. Right? 7 F orbitals. Okay, guys? So if I talk about first shell, in the first shell there is only one subshell. In that one subshell there is only one orbital, that's s orbital. Right? Let me quickly summarize all this. Whatever we have discussed till now, let me quickly summarize all this. See guys, if I talk about the first shell, n is equal to 1, represents what? It represents your k shell. If n is equal to 1, L value will be how much? 0 to n minus 1. L is 0. Every value of L represents the subshell. So, one subshell, which is called as S subshell. If L is 0, that means M is 0. Every value of M represents orbital. Which orbital it is? It's going to be S orbital. So, in first shell, there is only one subshell, S subshell. In S subshell, there is only one orbital, S orbital. Okay? Similarly, talk about n is equal to 2. N is equal to 2 means second shell, L shell. How many L values will be there? L can be either 0 or L can be 1. 0 or 1. Every value of L represents the subshell. So this is your S subshell and this is your P subshell. This is your P subshell. In S subshell, how many orbitals are there? If you talk about S subshell, if L is 0, M will be 0. If L is 1, M will be minus 1, 0 and plus 1. And every value of M represents an orbital. M is equal to 0, represents your S orbital. Right? Okay? M is equal to 0 here represents the S orbital. Perfect. And in case of P subshell, M is having 3 values and every value of M represents the orbital, so out of which one is going to be your, for example, Px, one is going to be Py, one is going to be your Pz. So if in total, if I ask you, in shell number 2, how many orbitals are there in total? In shell number 2, there are 1, 2, 3, 4. In shell number 2, there are 4 orbitals. In shell number 1, there is only one orbital. Okay? Talk about n is equal to 3. N is equal to 3. KLM. M shell. How many possible values of L will be there? 0, 1, 2. For L is equal to 0 represents your S subshell. L is equal to 1 represents your P subshell. L is equal to 2 represents your D subshell. Right? Now, for L is equal to 0, M will be 0. For L is equal to 1, M will be minus 1, 0 plus 1. For L is equal to 2, M will be minus 2, minus 1, 0, plus 1, plus 2. And every value of M represents the orbital. S orbital, Px, Py, Pz, Dxy, Yz, Zx, x square minus y square, and z square. So, if you talk about n is equal to 3, in the third shell, how many total orbitals are there? 5 plus 3, 8, 8 plus 1, 9. So, 9 orbitals are there. Right? Similarly, you can talk about the F subshell as well. Similarly, you can talk about the fourth shell as well. Okay? You can talk about fourth shell as well. So, I can generalize a statement. The statement is total number of orbitals in a particular shell is equal to n square. Total number of orbitals in a particular shell is equal to n square, right? Is equal to n square. And one more thing which you must know, which I already told you, maximum number of electrons that can be accommodated in a shell. How much that's going to be? That's going to be 2n square, right? Maximum number of electrons. Okay, leave that part aside. I do not need that here. So I hope this is clear. I hope this is clear. And before talking about the other things, there is one more quantum number. That's what you call a spin quantum number. That's what you call a spin quantum number, which is represented by S. Right? My dear students, electron while revolving around the nucleus spins also. Right? Electron while revolving around the nucleus, it spins also about its own axis. Right? That spin can be either clockwise or anti-clockwise. Right? Spin can be either clockwise or anti-clockwise. So S has two values, either plus 1 by 2 or minus 1 by 2. Plus 1 by 2 means the electron is moving with clockwise spin. Electron is moving with clockwise spin. Minus 1 by 2 here means electron is moving with anti-clockwise spin. Anti-clockwise spin. For example, this is the nucleus. Electron is revolving. And when the electron is revolving, at the same time, it's spinning about its own axis as well. It's revolving as well as spinning. Spinning Clockwise or anti-clockwise? For clockwise spin, S value is taken as plus 1 by 2. For anti-clockwise spin, S value is taken as minus 1 by 2. Okay? Right? So this was all about your quantum numbers. Perfect. Out of the 4 quantum numbers, 3 quantum numbers, the first 3, N, L, and M, they are derived from the Schrodinger's wave equation. The fourth one, that is the spin quantum number, it is not the outcome of the Schrodinger's wave equation. Right? Clockwise spin is sometimes represented like this, anti-clockwise spin is represented like this. Okay? Guys, now comes something very important. What is that? That is shapes of orbitals. How these orbitals exactly look like. Shapes of orbitals. We'll exactly see the shape of S orbital, the shape of P orbital, and the shape of D orbitals, right? F, their shapes are complex. We have got nothing to do with them. Okay? Now, first of all, S orbital. Let me talk about S orbital. S orbital, it is spherical in shape. That means around the nucleus, let's say this is the nucleus, around the nucleus you will see a spherical region. Around the nucleus you will see a spherical region like this, wherein we say the probability of finding the electron is maximum. And this spherical region around the nucleus, where the probability of finding the electron we say is maximum, you can call it as the S orbital. S orbitals are spherical. Okay? Right? S orbitals are spherical. A spherical region around the nucleus wherein the probability of finding the electron will be maximum. Right? Well, there is something called as boundary surface diagram, but I don't want you to go there, right? Okay, boundary surface diagrams, orbitals. Let's leave that part aside. Okay, if I talk about the P subshell, if I talk about the P orbital, let me tell you, P orbitals, they are dumbbell shaped. Now, how many P orbitals do we have? We have got Px, we have got Py, we have got Pz. How do you represent Px, Py, and Pz? Understand, guys. For example, if I talk about Px, see, let me make one Px over here so that you'll understand how this Px looks like. If I talk about Px, okay, Px, let's say, imagine this is your y-axis. Imagine this is your y-axis. Imagine this is your z-axis. Okay, y-axis, z-axis. So x-axis will be perpendicular to this plane. This is your x-axis. In case of your Px, electron density, or you can say the lobes, since your P orbital is dumbbell shaped like this, right? It has got 2 lobes, right? Both the lobes in case of Px, they lie along x-axis, right? So this is going to be one lobe. This is going to be one lobe, and this is going to be one more lobe. Perfect. So electron density is lying along x-axis. Perfect. My dear students, do you see this plane? Can you see this plane is cutting the orbital in such a way that no electron density lies on the plane? Do you see any electron density on the plane? There is no electron density on this plane, right? That plane which does not contain electron density, this imaginary plane, this is something which I call as nodal plane. And in case of, this was your Px orbital. In case of Px, the nodal plane is your YZ plane. Right? This is your nodal plane, YZ plane. Okay, wherein electron density is 0. Perfect. So this was your Px. Similarly, if you talk about your py, how this py looks like. This was your px. Perfect. This was your px. Now have a look on py. Again, simple. In the similar way, you can make it. I have to represent what? I have to represent py. So that means I have to represent the lobes along y-axis, right? Let's say this is your x-axis. Call this as z-axis and call this as y-axis. Call this as y-axis. Okay? And when it comes to py, the lobes will be along the y-axis. The lobes will be along the y-axis. The electron density will be along the y-axis. Perfect. This is how your py looks like. This is how your py looks like. Now, my dear students, do you see this plane over here? This xz plane? Do you see any electron density on this plane? No. When it comes to py, this is going to be your nodal plane. So, nodal plane over here are 1. And how do you designate this nodal plane? It is your xz plane, which is the nodal plane over here in case of py. Similarly, you can make pz as well, right? I believe you can make pz on your own, right? Pz you can make on your own. How many nodal planes will be there? There will be one nodal plane. And what will be that? That will be xy nodal plane. Perfect. Right? I believe this is clear. So this was your p orbitals. Similarly, how your d orbitals look like? How your d orbitals look like? How your d orbitals look like? Now, first of all, there are two types of d orbitals. One are called as axial d orbitals. Axial d orbitals. One is something which you call as non-axial d orbitals. Non-axial d orbitals. In case of axial d orbitals, let me tell you, electron density lies along the axis. Electron density lies along the axis. In case of non-axial, I would say the electron density, it lies between the axes. It lies between the axes, right? Axial d orbitals, here you'll be calling them as T2g set of orbitals. This is something which you call as EG set of orbitals. One is called as T2g set, one is called as EG set. Now comes the point. These d orbitals, I say these d orbitals are double shaped. Double shaped. These are double shaped. For example, let's say in total how many d orbitals we have? We have got dxy, we have got dyz, we have got dxz, we have got dx square minus y square, we have got dz square. We have got dz square. Right? We have got dz square. Let's just give me a second. I think this is the reverse which I told. This is T2G. Non-axial is T2G and axial is your EG. Right? Axial is your EG. Okay, so there are 5 d orbitals in total: dxy, dyz, dz, x square minus y square, and dz square. These 3 orbitals which we have over here, and these 2 orbitals which we have over here, right? These are what you call as non-axial orbitals. Non-axial orbitals, right? And the set of 3 orbitals, they constitute the T2G. We call this set of 3 orbitals as T2G orbital, right? And this is the axial one. This is the axial one. And this is something which we call as EG set of orbital. Now, how they exactly look like? First of all, as I told you, in case of non-axial orbitals, the electron density lies between the axes. Here the electron density lies along the axis, right? So, one by one, we'll check about them. For example, you talk about dxy. How does dxy looks like? Calling this as x-axis, calling this as y-axis. Okay? x-axis, y-axis. So the electron density will lie between the axes. This is how your dxy will look like. This is how your dxy will look like. For example, you have got dyz, dyz. Now, call this as y-axis, call this as z-axis. How does dyz will look like? This is how your dyz will look like. Double shaped. And this is the electron density which I'm showing over here. For example, you have got dxz, dxz, dxz. This is your x-axis, for example. This is your z-axis, for example. And this is the electron density which lies between these axes over here. This is your dxz. Perfect. Now, if I ask you, do you see any nodal plane over here? Do you see any plane on which electron density will be 0? See, I can cut this orbital in this plane, along this plane, about this plane, and on this plane there will be no electron density. Similarly, on this plane there will be no electron density. So in case of this d orbital, how many nodal planes are there? There are 2 nodal planes, right? Perfect. And what all these 2 nodal planes will be there? One is going to be your xz nodal plane, one is going to be your yz nodal plane. These are the 2 nodal planes which are here. These are the 2 nodal planes which are here in case of your dxy. Similarly, dyz, how many nodal planes? 2 nodal planes again. 2 nodal planes again. One is going to be your xy, one is going to be your xz. Over here, again there are 2 nodal planes. Again there are 2 nodal planes. One is going to be your xy, one is going to be your yz. Okay, right? 2 nodal planes. Perfect. Now guys, there is something called as dx square minus y square, which is the axial d orbital. So the lobes will lie along the axis. Along the axis. For example, this is your x-axis, this is your y-axis. The lobes will lie along the axis. Right? The lobes will lie along the axis. This is how your dx square minus y square will look like. Okay? Now, do you see a nodal plane? Yes, here is a nodal plane. It cuts the orbital in such a way that no electron density lies on this plane. This is one more nodal plane. It cuts the orbital in such a way that no electron density lies on that nodal plane. So how many nodal planes do we have? 2. One is going to be your xz, one is going to be your yz. Okay? This was your, I'm sorry, dx square minus y square. Now, one more is left, that is dz square. Now dz square, its shape is somewhat different. Its shape is somewhat different. See how it looks like. See how it looks like. All this is x-axis. All this is y-axis. So this is your xy plane. And over here, call this as z-axis. Right? Call this as z-axis. Now guys, first of all, you will find electron density over here along this axis. This is the electron density which I'm showing. Similarly, over here, you'll find electron density like this. Now, you must be thinking it looks like a PZ, right? It looks like a PZ, but there is something also missing. What is that? First of all, the electron density will be along z-axis. Apart from this, there will be electron density on this plane as well, like this. There will be electron density on this plane as well. This is how your dz square looks like. This is how your dz square looks like. Right? This is how their dz square looks like. Okay? This is your dz square. Now, in dz square, what do we have? In dz square, remember we have got 2 nodal surfaces. 2 nodal surfaces, or you can say we have got 2 conical nodal surfaces. We have got 2 conical nodal surfaces. And how they look like? Have a look. There will be one conical surface over here. This is one of the conical surface on which there will be no electron density, right? One conical surface and one more conical surface like this on which there will be no electron density. So two conical nodal surfaces are there. This is something which I would want you guys to remember directly from now onwards. So these were the shapes of your orbitals, which I believe all of you got over here, right? Perfect. Right, people? Now comes one more important thing. What is that? That is the calculation of nodes. That is the calculation of nodes and probability distribution diagrams. Understand what exactly I'm going to talk about. Understand what exactly I'm going to talk about. My dear students, first of all, what is a node? What is a node? How do you define a node? Node is basically a region around the nucleus. A region around the nucleus where psi square value is equal to 0. Or I can say where probability of finding the electron is 0. Region around the nucleus where the probability of finding the electron is 0. Okay? Region around the nucleus where the probability of finding the electron is 0. There is something called as nodal plane. What is a nodal plane? Nodal plane, it is a hypothetical plane. It is the hypothetical plane. Hypothetical plane passing through nucleus. Hypothetical plane passing through nucleus and no electron density lies on it. No electron density lies on it. Okay, that is the nodal plane. Now guys, let's try to understand every single thing in detail. Have a look. First of all, let me tell you, if you want to calculate the total number of nodes in an orbital, how do you calculate that? There is a formula. Total number of nodes is equal to n minus 1. This is the formula by means of which you calculate total number of nodes in an orbital. Total number of nodes. Now, these nodes are basically of two types. These nodes are basically of two types. One is called as spherical node. One is called as spherical node or the radial node. Or radial node. One is called as the angular node. One is called as the angular node. What is the spherical node? Right now, after some time, you'll get to know it in detail. Okay, I'll show it to you properly. Spherical node is basically a spherical region. Spherical node is basically a spherical region around the nucleus, wherein probability of finding the electron is 0. Right? A spherical region around the nucleus. A spherical region around the nucleus where the probability of finding the electron is 0. Angular node is basically a plane. It's a plane on which electron density is 0. How can you interpret this? Just give me like 4 to 5 minutes, you'll understand it in detail. But before that, I just want to give you certain results. First of all, how do you calculate the angular nodes? Just the value of L. Value of L gives you the number of angular nodes, right? Similarly, spherical nodes is given by the formula n minus L minus 1. N minus L minus 1, with the help of this particular formula, you calculate these spherical nodes. For example, let's say you have got 2s. Let's say you have got 2s. If I ask you what is the n value here, n value is 2. What is the L value here? L value is 0. L value for S is 0, right? So how many total nodes are there? Total nodes is equal to n minus 1. So 2 minus 1 is 1. Now, whether this node is spherical or angular, check it out. How do you calculate the angular nodes? Angular node is given by the value of L. And L value here is 0. L value here is 0. So this node, it is not angular. There are no angular nodes. So it has to be spherical. It has to be radial. N minus L minus 1. What is N? N is 2. What is L? L is 0. Minus 1 is equal to 1. So this node over here in 2s, it is basically a spherical node. So in case of 2s, you will find a spherical region around the nucleus where the probability of finding the electron will be 0. Where the probability of finding the electron will be 0 in case of 2s. For example, Let's say you've got 2p, or let's say you've got 3p. Okay, what is the n value? N value is 3. What is L value for p? L value for p is 1, right? If I ask you how many total nodes are there, total nodes, n minus 1. So 3 minus 1 is 2. There are 2 total nodes. Now, whether these two are radial, whether these two are angular, or one is radial, one is angular. How do you check it? See, spherical node is equal. Spherical node is equal to n minus L minus 1. N is 3 minus L is 1 minus 1. So it comes out to be 1. So therefore, angular node is given by the value of L. L value is 1. So there are in total 2 nodes, out of which one is spherical, one is angular. Right? Now, have the detailed overview of all this, what exactly I'm teaching you. Understand, guys, properly. So first of all, I'm starting with 1s orbital. I'm starting with 1s orbital. In case of 1s, if I ask you what is the value of n? N value is 1. What is the value of L for s? 0. How many total number of nodes are there? N minus 1. So 1 minus 1, 0. So there is no node. There is no node. There is no node. Okay, there is no node. Remember, guys, remember few things. For example, I want to plot a graph between psi versus r in case of S. Remember, all the psi versus r graphs as well as psi square versus r for the s orbitals. For s orbitals, they start from the top. Remember it directly. This is how you can ease out things. They start from the top. There is no node. If there is no node, first of all, the graph is going to start from the top. It is going to start from the top, and it is not going to touch the r-axis, because if it touches the r-axis, at that point, psi value will become 0. Psi becomes 0 means psi 0 represents the node, but there is no node as such in case of 1s. There is no node as such in case of 1s. Okay. Now, in case of 1s only, if you need to draw psi square versus r, now how do you draw the psi square versus r? Remember it directly. These are the shortcuts which I'm telling you. Is there any portion of this graph that lies down the r-axis? No. There is no portion of this graph that lies down the r-axis. So make it as such. Make it as such, like this. If there was a portion that was lying down the r-axis, what you were supposed to do at that time, that's something I'm going to let you know now. And how this 1s looks like, you know it. This is your nucleus. Around the nucleus, this is the region around the nucleus wherein the probability of finding the electron is maximum. So this is your 1s. This is your 1s, spherical. Okay, spherical. Perfect. Now, for example, let me talk about 2s. Let me talk about 2s. Let me talk about 2s. Understand. In case of 2s, the value of n is 2. What is the value of L? L value is 0. So how many total nodes are there? Total nodes, n minus 1. 2 minus 1 is 1. Now, whether this one node is spherical, whether this is angular, what is it exactly? Formula. How many angular nodes are there? The value of L. L value is 0. So angular node is 0. That means this node over here, it is a spherical node. It is a spherical node. So basically, in case of 2s, you will find a spherical region. In case of 2s, you will find a spherical region wherein the probability of finding the electron will be 0. So how do I show it? Let's say this is the nucleus. This is your electron density, first of all. This is the electron density over here. Now, after this electron density, you will find a spherical region wherein probability of finding the electron will be 0. And after that region, again, the electron density will start like this. This is the electron density now. So do you see in between one spherical region wherein probability of finding the electron is 0? This is the spherical region wherein the probability of finding the electron is 0. So this is your spherical node here. This is your spherical node here. Yeah? Perfect. Right, people? Now, how do you represent it? How do you represent it on the graph? For example, you have to make psi versus r first of all. Psi versus R. All the graphs for S, all the graphs of your psi versus R and psi square versus R, in case of S, they start from the top. There is one node as well, one node. So start from the top, there is one node. So the graph is going to touch the R axis at one point, like this, one point, and then it's not going to touch. This point represents your radial node, spherical node. Okay, that's all. Now from this, you can copy the psi square versus R graph as well. How you can copy the psi square versus R? How you can copy the psi square versus R? Is there any part of the graph that lies down the R axis? Yes. So leave that part aside. Rest make as such. So from here to here, it's going to be the same. It's going to be the same. Now, that part of the graph that lies down the R axis, take the reflection of this point, take the reflection of this part, take the reflection of this part along. See, it used to be like this. It was like this, right? But take the reflection of this part over here about this axis. Now, when you take the reflection, it will be like this. It will be like this. Now, you can remove this particular part. Remove this particular part. And over here, this is the point at which psi square value is 0. So this represents your node. And which node we are talking about? This is your radial node. This is your spherical node. Yeah? Perfect. So this was your 2s. Similarly, my dear students, you can make all these things for 3s as well. Right? Let's make all these things for 3s. If you talk about your 3s, n values 3, l values 0. Total number of nodes, n minus 1. 3 minus 1 is 2. Spherical nodes, or you call them as radial nodes. Angular nodes. Angular node is equal to L value is 0. So angular node is 0. So both these nodes are basically the spherical nodes. So in case of 3s, you will find two spherical regions. In case of 3s, you will find two spherical regions, wherein the probability of finding the electron will be 0. You'll find two spherical regions, wherein the probability of finding the electron will be 0. Right? Let me show it to you. Let's say this is the nucleus. This is your electron density here. Okay. Now, after this, there will be one spherical region. And after that spherical region, there will be electron density. So, till now, I have showed one node. Till now, I have showed you one spherical region, one spherical node. But we have to show two spherical nodes. So, one more spherical node and then electron density. Right? Perfect. So how many spherical regions are there wherein electron density is 0? First, second. So two spherical nodes here. So how do you show it graphically now? How do you show it graphically now? For example, I have to make psi versus R. When you make psi versus R, in case of S, psi versus R as well as psi square versus R, they start from the top, right? And there are two nodes. So the graph has to touch this R axis 2 times. So this is once and this is twice. Okay. And these 2 points, they represent your nodes over here, the radial nodes. Now, if you want to convert the same graph into psi square versus R, you can do it as well. Psi square versus R. Okay. First of all, from here to here, keep it as such. Keep it as such. This part of the graph is down the R axis. So take the reflection of it. Take the reflection of it. I've taken the reflection of it. Okay. Rest everything is same. Rest. See, this part is same. This part is same. I've just taken the reflection of this part. This point represents a node. This point represents a node. Which node? Radial node. Okay. I hope this is clear. I hope this is clear to everyone. So this was your 3S. Perfect. And in your NEET syllabus, my dear students, there is only psi versus R and psi square versus R for 1s and 2s. Only this much is in your syllabus. Well, you can make for P as well, but that's of no need to us. Okay. Is everything clear till here? Is everything clear till here? Now, one topic is left here, that is electronic configuration. But, my dear students, one thing I'm going to tell you. One topic, that is electronic configuration. I hope you all watched this particular session, that is periodic classification part 1 taken by ma'am, right? Sonali ma'am. She has discussed the electronic configuration over here in detail. She has discussed the electronic configuration. She has taught this topic here. So I would want you guys to complete electronic configuration part here, right? Okay. She has given the idea about quantum numbers as well, which I told you right now, which I was teaching you. And here, this is the electronic configuration. Let me show it to you. Electronic configuration rules, Bohr-Bary's rule, right? And then you have got Hund's rule, etc., etc., Abbas principle. Perfect. So here she has taught you how to write the electronic configuration in detail. So electronic configuration part, I'm not going to teach you here. That's already done by ma'am here in this particular lecture. Okay, right? So do it from here. Do it from here. Perfect. And electronic configuration, you know, it's one of the easiest topics, right? Perfect, guys. And the ones who have not studied the atomic structure part 1, I would want you guys to cover it from here. Go to playlist. Once you go to the playlist, drag it a little down, and here you can find the complete chemistry playlist. Click on it, and here you can find atomic structure part 1. Okay, and today it was atomic structure part 2. So with this, your whole chapter of atomic structure is done and dusted. All right, and my dear students, one more important thing. One more important thing. What is that? Day after tomorrow, we are starting a new chapter. We are starting a new chapter, and that new chapter is going to be your chemical bonding. So chemical bonding part 1, I'll be doing on 14th of August, exactly at 7 p.m. In 3 sessions, I'll complete the chapter chemical bonding in detail, like we complete all the other chapters, right? So this particular session, I would want you guys to join in to this particular session. And right after watching this particular session, do smash on notify me and do smash on the like button as well, so that I get to know that you guys are interested to study this particular chapter as well. Okay. So chalo, with this, go for MTG. There is no need to solve NOS3. Thank you, Thaswin. Thank you. Thank you so much. Hello, guys. With this, I'll be taking a leave. I'll see you guys day after tomorrow with the new chapter, that is your chemical bonding. Right? So take care. God bless you all and love you all, guys. Bye-bye.